This is a short video on how to find the difference between two population proportions, or based on the samples of two populations, if there's a difference between those two. We're going to do a confidence interval and a hypothesis test here. So we're going to start with the hypothesis test. So this is actually from your book, section 9.2, number 3 is the example. And what we've got here is a treatment group and a placebo group. And this might be the proportion of people that had side effects or something like that. So the treatment group had a rate, if you take 100 divided by 1,000, is a 10% rate of, let's say, side effects. And then the placebo group, the ones that didn't take the medicine, had a 0.125, and it doesn't say what we're doing here, but all we know is there's two sample proportions, and this is binomial, like either they did or did not. So our null hypothesis always with difference between two proportions is that there's no difference. Our null hypothesis is that P1 is equal to P2. And remember, if it says P, it's the population proportion. So between these two populations, treatment group and placebo group, they're two different populations. Our null hypothesis always has equal, so assuming equal population proportions. The alternative is that they're not. This one doesn't really indicate either one is greater than or less than the other. In this one, we're going to go ahead and do the z-test for difference to proportions. And I'm going to pull up the formula sheet here so you can see this. So if we go to hypothesis testing, and we have, so the first question always is it a hypothesis test or confidence interval? So we're doing hypothesis test. Second one, is it means or proportions? We're doing proportions. And then the question is it one or two samples? Well, we have two samples here. So here is our formula for the difference between two population proportions. So there's P1 hat and P2 hat. Remember, if it's hat, it's the samples. So the difference between those two, and we're assuming that the difference between P1 and P2 is 0. So this part is going to be 0. And honestly, for all the examples in this course, our null hypothesis is going to be equality. So this is always going to just be a 0 here. If you did know ahead of time there was a difference in the populations, you could account for it there. And then here is the measure for the standard error between those two different proportions. And we are doing unpooled. Pooled means you would actually combine these two. And it actually says pooled estimate here in your text. And if you look at the example, it will show that one. But honestly, the difference between pooled and unpooled is going to be very negligible, hardly any difference. So the way we're going to do these is unpooled, which means we're going to kind of separate P1 and P2. If it's pooled, the difference, I've written it up down here, is you add the successes and you add the total trials. So the only difference is a small, very small difference. Instead of using like 10.1 and 0.125, you just use this 0.1080 and put those numbers in here, and the difference is almost nothing. So just to be safe, we're going to use unpooled estimates here. Oops, sorry. So we go ahead and we calculate this difference, calculate the standard error, make sure you take the square root after you do everything under the radical, and we get negative 1.44. That means the difference between these two sample proportions is 1.44 standard errors apart from each other. If we draw a picture of that, you can kind of see where negative 1.44 is. We look that up on our z-table, which I'm assuming you can look up negative 1.44 in your z-table, and we get this 0.0749. So that, and then since it's equal and not equal, the not equal means it could be greater than or less than. So we're calling this a two-tailed test, which means then we double this proportion. So if we would have had one, it didn't matter what order we did this in, if we flip-flopped those two, and we got positive 1.44, we'd still get the same area here, but we have to double it to account for it, either positive or negative. So the probability we would get this much difference by random chance is about 15%. So there's about a 15% chance you would get this much difference by randomness. And so the question is there really a difference between these two? And if you see here, our significance level is 0.05. That means we have to observe something that only happens less than 5% of the time before we're going to say there is a significant difference in these two proportions. And since our p-value is bigger than 0.05, we are not going to reject the null hypothesis. If it was less than 0.05, then we would. But in this case, we don't have enough evidence to say there's a significant difference between the treatment and placebo group. And then we explain that in context. There's not a significant evidence the proportions are different. So here is a hypothesis test for the difference between two proportions. Again, we're not going to use pooled. I have written it up as pooled here, or just show the example. I didn't calculate the z-score. The z-score is almost identical to this, and this will do you well. So in your homework, do it this way. If you need to go more accurately, you can use StatCrunch, but this will show the method to calculate the hypothesis test for the difference in two proportions. To describe the type 1 and type 2 errors here, a type 1 error is when you reject the null hypothesis and you're wrong. So in this case, we'd say, yeah, there's a difference between these two, but then we'd be wrong. That'd be a type 1 error. A type 2 error is if you do not reject, like we did here, and we're wrong. So we don't know if we're right or wrong, but that's why it's called an error. If you knew you were wrong, you would change your mind. But so let's say hypothetically in this one we said, yeah, there's not enough evidence to reject. We do not reject the null. But let's say in reality there really is a difference that we just haven't measured or don't have enough evidence for. That would be a type 2 error. And alpha level is the percentage of time you're willing, that you're going to accept type 1 errors, the percentage of the time that you would reject and be wrong. And then type 2 errors is beta, which is not is obviously the lower the alpha, so the fewer type 1 errors, the more type 2 errors you will make. And if you try to lower type 2, you'll increase type 1. So hope this helps with difference of two proportions, and make sure, and remember when we're using proportions, we're just going to always use our z table.